There we go. Okay, so as I just said, we are going to now use math to discuss the rates of reactions. And so they're going to relate the concentration of the reactants to the rate of the reaction. So rate laws depend on reactants, not the products. And so we're just going to start. I'm going to show you what this equation looks like. That's what's bolded here. This is what we call a generic rate law equation. And this is based off of an equation A plus B goes to C. Now, defining these variables, you may not know every single word I say, but we're going to dive into each of the variables. But in this rate law, K is what we call the rate constant. When you see A with brackets around it, that represents what's called the molarity, which is a fancy term for the way that we talk about concentration. So how much is in solution of reactant A? If you see brackets B, same idea, the molarity or concentration, I'm just going to abbreviate that as CONC for now, of reactant B. We then have exponents N and M. These are what we call reaction orders. So N is the reaction order of A. M will be our reaction order of B. So now we're going to break down rate constants, molarity, and reaction orders. But these are the three parts that we put in our equation to tell us what our rate is. So starting with the rate constant, we use letter K. You always see it as letter K. And each reaction gets its own constant associated with it, and it's dependent on temperature. So rate constants can be given values, but we also are going to be determining them using data, experimental data. Then we have molarity. And so molarity is just a way to express the concentration of a solution, but it has specific units. So the units of molarity are our friend moles. So it's how many moles are in a liter. So it's moles per liter. We can write this also as MOL over L. You might see this as MOL times L to the negative first power, which means the same thing. Or sometimes people write it as capital M. So this means molarity. It's just a measurement of concentration. Reaction order. This is the exponent. So this is the little N or M. And this has to do with the magnitude of effect that changing that reactant's concentration has on the rate. So let's see that reactant really affects the speed. It's going to have a higher exponent because it's going to take into consideration its concentration a little bit more than if it didn't really have any effect. And so we can also find what's called the overall reaction order. And this is just the sum of the exponents. So if we had, for example, exponents of A1, B2, the overall order, our overall reaction order is third. So you would just add 1 plus 2. If this was our generic equation. So overall reaction order, piece of cake, no problem here. And so what we're going to be learning is that how to find out the orders or the rate constant. So that's what we're going to be practicing today. Again, I want to point out, was reaction C in this rate, general rate law expression? We don't care about products in here. That doesn't affect the amount of product that we will make. So for rate laws, we just look at reactants. All right. So when I started making these notes, I started typing up a bunch of boring stuff about how it works. No, let's just get into it. Let's just start some problems. I think it's the easiest way to understand. Now, this math is not hard. It's just weird. This weird math. So I am confident that you guys will get it. It just, like I said, I think doing problems will be the easiest here. So when we are determining the orders of the exponents of our reactants, we do this using experimental data. So you guys will see a lot of these tables that tell you, okay, we have multiple trials we did of the experiment. These are the different concentrations we used of reactant A. These are the different concentrations we used of B. And here are the rates that we got. And so when we mix these together, they form C. So we're going to pretend that we still have a generic equation that A plus B goes to C. This is what our representative equation is. So when we go to write a rate law, we always start writing our rate is going to be equal to some rate constant K. And then we have to consider the concentration. So we use those brackets of reactant A. And we don't know what its exponent or rate order will be yet, times reactant B's concentration to some order as well. So this is kind of a good step to point yourself in the right direction. Okay, generically, we're going to figure out what these generic K, N, and M values are step by step. So first, let's start with the reaction order for A. So really, we're solving for N in this case. So what you need 2 trials where the concentration of reactant B remains the same. Because if we're trying to see the effect A has on the rate, we don't want to be changing 2 variables. We want to control one. So keeping B constant, we control that variable and see the effect that only A has on the situation. And so that being said, not only do we need to find one where B remains the same, but we need to find one where A changes. And so what we're looking for, what this N will be is, does it double? Then it's a 2. Does it triple? Then it's a 3. So it's just depending on what happens. We are determining the exponent depending on what I call it, the factor that it changes by. And so what we do is we divide the larger concentration by the smaller concentration, and we do this in comparison to the rates as well. So I'll show you how we set this up. First, we have to determine though, which 2 trials does B stay the same and A changes? 1 and 2, great. So we are going to use trials 1 and 2. So I'm going to say, just for note's sake, trial 1 and 2 fit parameters. Now, my hint to you is I'm going to set up a generic equation, and then I'm going to tell you, I always put the larger concentration on top. So the trial with the larger concentration. I'll show you what I mean here in a second. So what we're doing is we are going to take the concentration of A. In our case, I'm going to put of trial 2, because if we're looking at these 2 trials, which has the larger concentration of A, 2 or 1? 2. So to make the math easier, if you always put the larger one on top of the 2 you're comparing. So I'm choosing to put concentration from trial 2, the concentration of A then to trial 1. So these are the 2 trials I'm comparing. These are going to be to some power N. N is what we're solving for. We're going to set these equal to the rates of those 2 trials to see in what order it's changing. And so what's important here is you need to keep the same order. You have to put the rate of trial 2 on top and the rate of trial 2 on bottom, or trial 1 on bottom. So you need to make sure that these are in the right order, that the trials match. Keep that consistent. So when we go to sub the values in, the concentration of A from trial 2 is 0.10. That is going to be divided by the concentration from trial 1, which is 0.050, parentheses, and N is what we're solving for. So again, I am going to make a note here, and you guys can do the same thing if you want, is that we put the larger concentration on top. And so this will in turn be equal to the rate from trial 2, which according to the table is 8.0 times 10 to the negative third power. Divided by trial 1, 4 times 10 to the third power. Negative third, sorry, I keep trying to say that. So what this turns into is going to be 0.1 divided by 0.05 is 2. You can put that on your calculator, or you can just look at it and realize that 1 is twice as big as 0.05. So we have 2 to the nth power is equal to 2, because 8 times 10 to the negative third divided by 4 times 10 to the negative third is also 2. So what is n equal to? 1. So since n is equal to 1, that is now a reaction order for reactant A. So where we sub this in at this point of our generic rate equation, so I'm just going to write this again with n subbed in, is rate is equal to our constant times the concentration of A to the first power. And we still don't know B, so I'm going to leave B's as M. So our newest addition is this one here. All right, any questions on this procedure? Like I said, it's weird, but it's not necessarily a difficult problem. Okay, now, so orders affect, so like, for example, if you add two reactants, one might dictate the speed of it more than the other. So you know, oh, it matters more if I put more concentration of one thing in versus the other, because if I want my reaction to go faster, I'm going to add it of this one. Or when it comes to figuring out rates, this is helpful for even like more like biochemical stuff, to know how quickly your body does processes and like what kind of orders things are. That means then it means that this rate is really dependent on whatever the second reactant is. Any other questions? Okay, let's figure out the order of B. So same idea, except now we need to find two trials where B changes and A stays consistent. So what two are we using here? Wonderful, we're using 1 and 3 to find B. So if we go here, now we're gonna put T3 on top because that has the bigger concentration of B. And so I'm gonna put here though that we choose trial 1 and 3. Okay, so we have the concentration of B from trial 3. We're going to divide that by the concentration of B from trial 1 to the nth power. Set that equal to the rate that happens from trial 3 divided by the rate that happens trial 1. Plug values in. You would get 0.10 divided by 0.050. So the nth power is equal to 1.6 times 10 to the negative second power divided by 4.0 times 10 to the negative third. This is 2 to the nth power is equal to 4. So what does M equal in this case? 2. So this has a reaction order of 2. So now we're able to sub this in to our generic rate law, and we get that our rate is equal to K times A to the first power times concentration of B to the second. So K is rate constant, and that's actually the, so K is like a, yeah, yeah, yep. So we're gonna actually figure out what K is for this reaction now. So I know you guys won't have a table on this page, but I promise you I'll use good numbers here. So when we're figuring out K, we already know that rate is equal to K times A to the first, B to the second. If we take any trial, we're given a rate, we're given the concentrations that make that rate. So we have all the other variables except K. So we can solve for K and then just plug in numbers for one of the trials and get an answer for it. So if we want to solve for K, we are just gonna move these terms to the denominator on that side. We get that K is equal to the rate over A to the first power, B to the second. Now, I'm gonna use units now, and the units are gonna be weird. And the units are gonna change depending on what orders these reactants are. So the reason why I didn't use units for the first parts is because we just made ratios, they cancel out no matter what you did. This, we will be using units though. So with this equation, if we plug in, for example, let's plug in trial 1. I'm just gonna put plug in trial 1 data. We get that K is equal to, the rate that was given was 4.0 times 10 to the negative third moles divided by liters seconds. Our concentration for A for trial 1 was 0.05 units of moles per liter. And this is to the first power. Then we have the concentration of B, which was also 0.05 moles per liter, but this was to the second power. So put this in your calculator and you would get 32 as your constant. And our units would be liters squared over moles squared times seconds. How you get that is if I break it down with just the units, you'd have moles over liters times seconds all over moles per liter times moles per liter squared, right? You guys follow me so far there? I'm just looking at the units. This moles per liter would cancel out with this moles per liter. So you would be left with 1 over second divided by moles over liter squared. Don't cry, flip and multiply. So you get 1 over second times the reciprocal of moles per liter squared, which would be liter squared over moles squared. And if you combine those, you get those units. So, yes. Yeah, but you can in a way, in a sense that if you remember that liters squared, or liters always will be on top, you'll always have moles per second on the bottom. And depending on what order you have will affect if it's the liters and moles are squared third. So what's the overall reaction order for this one? The reaction order though is 1 plus 2. So it'd be third order. So that's when you add the exponents together. So the overall reaction order is 1 plus 3. So this is, or sorry, 2. 1 plus 2 is equal to 3 because this is N plus M. So I'm adding together these to get the reaction order. So now you can associate that an overall reaction order of 3 will get you L squared over mole squared times second. If you had an overall reaction order of 2, it would just liters per mole. So it's minus like an exponent in a sense from the 2. But you'll always have either second or sometimes we do it in minutes too. What's up, Brian? Why do we have to figure out, hey, if we're That's a separate question. Oh, but that's a good question. They're separate, but they're both good textbooks. So if you saw the overall order, I mean, I guess that. Okay. Well, yeah, you know that before you saw it. Yeah. That was just to answer, like, if you want to be strategic. And that's just another question to ask. So you don't need to know K before you know the overall reaction order. All right. We are going to do one more practice together, and then your problem sets will be 3 separate practice problems. All right, let's do this one. Yeah. Yes, but it could, your unit of time could be minutes too, or hour. You know what I'm saying? So like, but that will always stay as like just 1 on the denominator. Okay. Now we're going to look at the reaction Q plus X goes to some products, because guess what? We don't really care about the products, so it doesn't matter. So in this case, we're going to write our generic rate law for the equation. We have that our rate is equal to some constant times the concentration of Q to some power times the concentration of X to some power. So I'm already going to apologize ahead of time. This is going to be a little cramped. So to those of you that write big, be strategic. I'm sorry. So figuring out the reaction order for Q. This is when we set up the 2 trials where the other one is constant. So we got to find 2 where X is constant. Those luckily are trials 1 and 2 again. And trial 2 has a bigger concentration of Q. So we're going to put that on top. So we are going to write that we are going to take our Q from trial 2. We're going to divide that by our Q from trial 1. That's going to be to some power equal to rate of trial 2 over rate of trial 1. So if we plug in our numbers, we get 0.24 divided by 0.12 to the nth power. That is going to be equal to 3.0 times 10 to the negative 3rd divided by 1.5 times 10 to the negative 3rd. So what you'll get here is we have a 2 and is equal to 2. So n equals 1. Now let's take the time to sub in or figure out for X. For X, we're going to use trials 1 and 3. And so we are going to put trial 3 over trial 1 in this case. So we have concentration of X from trial 3 over the concentration of X from trial 1 to the nth power equal to rates of trial 3 over rate of trial 1. Sub in your values, you get 0.20 divided by 0.10 m is equal to 1.2 times 10 to the negative 3rd all over 1.5, or sorry, negative 2nd, my bad on that. 1.2 times 10 to the negative 2nd divided by 1.5 times 10 to the negative 3rd. This gives us 2m is equal to 8. What is m equal to here? Yay, 3, we can do exponents. M is equal to 3. So I'm gonna hop up this way and it's asking us to write the rate law expression with the subbed orders and then the overall order. So our new rate law will be rate is equal to K times Q to the 1st power times X to the 3rd. And what's the overall order? 4. It's a 4th order equation. Now the next step here, we are going to solve for our rate constant. So this is again where we're going to take our rate is equal to K times Q times X to the third. Solving for K, we get that K is equal to rate over Q times X to the third. I'm not going to be super picky if you guys do or don't write the first power for once it's subbed in like this. If I'm asking you if it's first order, please write it in, but like for solving for K, that's fine. Anyway, here, let's just pick problem 1 because why not? We're going to sub in 1.5 times 10 to the negative third moles per liter times minute all over 0.12 moles per liter times 0.10 moles per liter to the third power. This is going to give us 13 liters to the third power over moles to the third power times minute. Any questions on this so far? Got one more application for you, just as easy as plugging stuff in. But I might ask a question saying, okay, what's the rate if we know K already? And here are 2 concentrations to try. So we just solved for K. So what you would do in this problem is just rate is equal to your new K we just found, L3 over mole 3 times minute times the concentration of 0.12, or sorry, yeah, it wants 12 mole per liter, and the concentration given of 0.015 moles per liter to the third power. Calculate that out, we get 5.3 times 10 to the negative 6. Have fun, guys. Moles per liter times minute.